In today's video, we dive into how modern logistics teams use AI to decide both the shipment mode and the specific carrier when operations span standard, non-standard, and temperature-controlled flows. The core shift is moving from a single, fixed model to a layered decision engine. At the prediction layer, interpretable machine learning learns the complex, non-linear interactions between shipment attributes, promised service levels, and network conditions to estimate the likelihood that air, road, rail, or sea will meet the cost-service frontier. On top of that, a policy layer translates company priorities into trade-offs so that KPIs like OTF, temperature integrity, and emissions targets are not afterthoughts but first-class constraints. This layered approach is what makes AI actionable for carrier selection rather than just a dashboard curiosity. To understand why machine learning helps, think about how real shipments behave. The effect of weight or cube is not linear. Urgency changes the tolerance for cost. Consolidation options shift when the network is saturated, and a carrier's on-time probability is conditional on lane, weekday, and weather. Interpretable ML unpacks these interactions. Using tools like SHAP, planners can see why the model favors rail for medium-distance ambient freight on Tuesdays but flips to road when dock congestion spikes. That transparency matters because operations teams adopt models they can question, not black boxes that simply output a label. However, prediction accuracy alone does not guarantee good decisions. The second ingredient is a principled way to merge forecasts with business rules. This is where multi-criteria decision analysis earns its place. By structuring criteria, cost, time definiteness, reliability, claims history, carbon intensity, into a weighted utility, the organization encodes its strategy. The AI contributes the live estimates for each criterion, while MCDA ensures the chosen option reflects policy. For temperature-controlled chains, for example, reliability and temperature excursion risk can dominate the score, so even an apparently cheaper ambient option is filtered out before it reaches the dispatch screen. Let's bring this down to a practical workflow. Each tender is scored across modes with expected delivered cost, on-time probability, service variance, and risk of failure. For carriers within the winning mode, a second pass ranks providers using lane-specific reliability, dwell patterns, and recent performance signals. When the network shifts, say a hub outage or a capacity crunch, the model updates the expected variance and points the decision toward resilient alternatives. Importantly, users see the reasons. A change in dwell at a cross-dock, a deterioration in refrigerated trailer availability, or a sudden spike in claim rates. That visibility accelerates trust and reduces second-guessing. Implementing this in a mid-sized operation usually starts with a clean data backbone. You'll need consistent shipment histories with timestamps, service commitments, actuals, and exceptions. A carrier ledger with lane granularity, and event data like dwell, handoffs, or temperature excursions. Many teams start with gradient-boosted trees as the baseline because they perform well out of the box and remain interpretable with post-hoc explainers. From there, a simple policy layer, AHP or TOPSIS, lets you weight criteria explicitly so commercial priorities like seasonal OTF or penalties on pharma lanes are represented numerically rather than negotiated case by case. For last mile and volatile lanes, hybrid approaches add even more value. A learning heuristic can feed candidate sets to an optimizer, shrinking the search to the combinations most likely to meet service and cost constraints. When demand spikes, the model favors carriers with slack and lower dwell variance. When service failures appear in a micro-region, the weights shift automatically to providers whose recent reliability remains stable. The result is fewer expedites, fewer claims, and a measurable uplift in first offer acceptance. A frequent concern is governance and bias. If your data overrepresents a few lanes or one dominant carrier, the model may unfairly favor the familiar. Mitigate this by monitoring feature drift, holding out lanes for true generalization tests, and using constraint-aware policies that cap exposure to any single provider or route until fresh performance data accumulates. Equally, treat the AI as a co-pilot. Let dispatchers override with reason codes that the system then learns from, so institutional knowledge feeds back into the model rather than living only on the floor. Finally, measure what matters. Before and after trials should compare OTIF, tender acceptance, cost per kilo, claim rates, and planning time. For cold chain flows, add excursion frequency and lane level variance. If the AI truly helps, you should see a sustained improvement in reliability at the same or lower cost, and fewer firefights to recover late or damaged loads. That's when the technology stops being a pilot and becomes the operating system for mode and carrier selection. Thanks for watching today's video. I hope you found it helpful and insightful. If you enjoyed it, hit the like button and subscribe to Logistics ABC. Turn on notifications so you never miss out on future videos. Check out the recommended videos here for more great content. Thanks for being part of the Logistics ABC community, and see you in the next video.